to have Professor Yoshihiro Iwasa from University of Tokyo to come give the first condensed matter seminar of the term. So welcome back to school, and we're very glad to have Professor Iwasa here with us. He's a big pioneer in 3D materials. You know, some of his very famous works. You know, a lot of the PhD students will know. He pioneered, for example, using ionic liquid gating in two-dimensional materials to be able to see very nice signatures of superconductivity in TMDs. Works extensively in excitons, works in photocurrent, works in a whole host of things, and has received numerous prizes for his work. So without further ado, let's welcome Professor Iwasa to the condensed matter seminar at NTU, please.
Thank you very much, Justin, for a very kind introduction. And also, it's a very good opportunity to join this seminar. You said this is the first seminar in this semester?
In this semester, yeah. So we just started this semester, and so, you know, I think week one was either this week or last week or something like that. And we typically start on week 2, and so it's the first in this series in this semester.
Okay, yeah. Thank you all of you for joining this my seminar. So my name is Yoshihiro Iwasa from University of Tokyo. I'm going to speak about the two-dimensional BCS-BEC crossover in layered superconductors. I have been working on 2D materials, but also in the ionic liquid gating induced superconductivity. So this is a kind of merging activity in our group. So we are working on the with many colleagues. Particularly, this is my picture, our group's picture taken in a couple of years ago already. And the main work has been carried out by Yuji Nakagawa, our former PhD student. And also the sample came from Hiroshima University and Kyoto University. And the theory support is obtained from my colleague at the University of Tokyo. So let me start with Bose-Einstein condensation in Fermion systems. I believe all of you know what the Bose-Einstein condensation is, but the topic today is on the BEC of fermions. So fermions could form a pair, which is regarded as a boson, and which could show a textbook like a Bose-Einstein condensation. The examples of these Bose-Einstein condensation in fermion systems are somehow these 4 families: neutron stars, so nuclear matters, and the superconductors, helium-3, and cold atoms. And of course, in the lab, most of the experiments have been carried out in superconductors and cold atoms. But importantly, real systematic experiment on the BCS-BEC crossover has been carried out mostly in cold atoms. So this is a neutron star pictures, and most of these are done in theoretically. So as you see here, the condensation temperature is extraordinarily high. It's impossible to access in the lab, but below these temperatures, these 3 materials we can deal with in our lab. So the BEC in the potassium 40 has been realized in 2004 simultaneously by these 3 groups independently, and the number of at that time their number of the atoms is particles is in this order, and the temperature is much lower than 1 microkelvin, much lower than our case of superconductors. So this is the somehow predicted theoretical phase diagram connecting BCS-BEC, BEC and BCS. So basically, for condensed matter physicists, the superconductivity is very, very popular. We are very familiar with this phenomenon. And here we see Fermi liquid condenses into the BEC-like state, in which the boson somehow condenses directly from the unpaired fermionic liquid state. But in the other end, BEC region, they form the boson, two pairs of electrons, which is boson already at the even very high temperature, but it is not shown. It doesn't show any condensation, coherent state. But as you learn from the statistical mechanics, if you cool down the boson temperature, not only boson but also all other particles, the thermal de Broglie wavelength is getting larger and larger, and then this means that the coherence somehow expands by lowering the temperature. If the coherence length reaches the interparticle distances, they form somehow macroscopically coherent state, which is nothing but Bose-Einstein condensation. So, so this, as this picture says, the BEC has a very serious overlap between the fermion pairs, but in the BEC state, the density is much less, and the Cooper pair, boson scale is much smaller than usually smaller than the interparticle distances. Then these two are somehow continuously connected by changing some parameters. In the case of cold atoms, they are able to change the interaction strength by using a very special method in their case. So just take a look at the case of cold atoms. They are able to confine the fermion gases such as potassium-40, and in these numbers, and they are able to cool down by using the laser and some magnetic field confinement. And this is a real picture, and they are able to confine in a very small, very tiny space, and they can measure many things in such a tiny regions by using laser spectroscopy. Very strong point of this cold atom is that they are able to change the strength, interatomic interaction. In their case, they call it scattering length, using the Feshbach resonance. So they are able to change the this scattering length by changing the magnetic field in such a very small magnetic field. And they are able to change the scattering length, sign of the scattering length. And with this change of scattering length here, Kf is the Fermi momentum, A is the scattering length tuned by this Feshbach resonance. They are able to see some phase diagram. This color mapping is the height of this condensation of this distribution, which shows nothing but how densely the BEC occurs. So they are able to see this type of phase phenomena, although the signal to noise ratio is very bad, but they claim they are able to see BEC, not only BEC, but crossover to BCS regions. So this is a case of the cold atom. But if you look back this phase diagram and think about the superconductors, superconductors basically is existing around the BCS limit. Most of the superconductors are existing in the BCS limit. But as you know, interaction between the pairs, we are not able to control. It is basically controlled materials itself. So how we control the crossover from BCS to BEC? The strength of this superconductivity is we are able to tune the carrier density relatively continuously. In the bulk, we are able to somehow make alloys or chemical substitutions so that we are able to tune the carrier density. And also, nowadays, we know that we are able to control the carrier density by field effect gating. So this is the very basic cartoon of the field effect transistor structure we use. And also, you know, this is the very fundamental device for our society, high-level electronics society. So this is a semiconductor and metal electrode, and which sandwiches the insulators. So if you apply the gate voltage between these two electrodes, the charges are accumulated in this manner. So this is nothing but a capacitor, you know. So if you measure the conductivity here between the S and D electrodes, and since the charge can be controlled, electron density can be controlled by the gate voltage, the conductivity along this channel can be dramatically controlled from insulator to somehow conducting layers. But so if you increase the gate voltage and increase the carrier density, you are able to make a insulator superconductor, conductor or superconductors. So nowadays, two routes for gate-induced superconductivity is already known. One is the ionic gating, which we have somehow started almost more than 10 years ago. And the second one is the twisted bilayer graphene, which is somehow very, very popular nowadays in our community. So this method, first method, is replacing a gate insulator with a special gate insulator, which is ionic gel or ionic liquid. And in this latter case, we replace the normal semiconductor with a very special semiconductor that is a twisted systems. And with these twisted systems, you are able to have a very large lattice constant, and so that the effective carrier density can be relatively large, even though the real carrier density is not that large, but effective carrier density is large. Effective carrier density means how much electrons do they have per unit cells. So unit cell is huge due to the more superlattices. So putting 1 electrons per unit cell, such a large unit cell, can be done using in a conventional field effect transistor device. So if you compare the conventional transistor device with our ionic liquid gated device, so-called electric double layer transistor, we replaced this insulator with ionic liquid. So let's say this is the salty water. So sodium chloride is dissolved in water, And then if you apply gate voltages, so the sodium ions are accumulated on top of the semiconductors. Then in order to screen the Coulomb potentials from the sodium ions, the number of the charges, electrons, are accumulated on top of the semiconductors. And the distance between the sodium ions and the electrons are very, very narrow. So which has a huge capacitance comparing to the conventional field effect transistor, so that we are able to accumulate 1 or 2 orders of magnitudes higher carrier density comparing to the conventional FET. That's why we are able to access metal, not only metals, but also superconductivity. So this data showing a very typical temperature dependence of a resistivity curve with different gate voltages. So without applying gate voltage, it shows the semiconducting behavior. But once you apply gate voltages, resistance drops dramatically and finally tuned into a superconducting state. So this is the phase diagram determined by this RT curve, and the TC versus carrier density measured by the Hall effect, right above the transition superconducting transition temperature. So we start with the insulator. After somehow several large region of metallic state, we enter into a superconducting state and making some superconducting dome. But if you compare with that of the twisted bilayer graphene, we realize that the same thing is occurring. So now this is somehow one of the somehow state-of-the-art phase diagram of a twisted bilayer graphene. This is a charge neutrality point, kind of insulating state, and they are able to change the superconducting state and several superconducting states by changing the carrier density. But please look at the scale of the horizontal axis. This is 1 times 10 to the 12. So this is a 13. And since this is 10, it is in the order of 10 to the 1 times 10 to the 14th. So the scale between these two is different from 2 orders of magnitude. But if you look at this part, now we start from a charge neutrality point, which is insulating and coming into a metallic state, white metallic state, entering into the superconducting state. This is nothing but what we see here in this phase diagram. So now you realize that why people are excited with this. So with just a small number of electrons, you are able to change many phases depending on the band filling. But here in this case, we see only 1 band filling. This can be the good point of this method is that we are able to apply this method in relatively normal materials, not a special semiconductors. With this ionic gating or electric double layer transistor device, we have worked on many materials and reviewed some symmetry related physics. So now we are working on low symmetry materials. For instance, if you work on the MOS2, it is a trigonal materials. It shows somehow Ising superconductivity. It shows a very peculiar behavior. Also, we apply electric field, which inherently induces the symmetry breaking perpendicular to the plane. So we see some non-reciprocal transport in the superconducting state. Another interesting thing is that since you have a very highly crystalline state and just almost monolayer superconductors, so relatively clean state, And so this is a very good platform to investigate how vortex behave in such a clean state. So Justin, you have a question?
Oh yeah, no, you should continue. I just had a question about your non-reciprocal transport. Was this in a Josephson junction, or was this in some other kind of
No, this is just a simple superconducting material itself is non-central symmetric.
Yes.
So you mean, are you talking about the vortex matter?
No. I was talking about the non-reciprocal transport. Yes.
So here, for instance, in this Ising superconductivity. So if you think about the MOS2 and doped into somehow K point, case in the top of the bottom of the conduction band. So spin is polarized perpendicular to the plane, yes. Right? And this forms a Cooper pair.
Yes.
Then the spin is always polarized along this perpendicular way. But if you apply magnetic field in plane,
yes.
So spin is locked in perpendicular to the magnetic field. Yes. It's very difficult to follow the external magnetic field.
Yes, that's right.
This polarization for certain up to a very high magnetic field.
Yes.
So as you know, effective magnetic field or internal magnetic field by this Ising type spin polarization reaches about 1,000 Tesla or at least 100 Tesla.
Yep.
So the superconductivity is very, very robust yes. Against the in-plane magnetic field. This yes. is somehow a very peculiar feature of the Ising superconductivity, which is very rare to see.
Yes, that's right. So I understand that. But what does that have to do with the non-reciprocal transport?
Oh, I see. So then, so the particularly in this non-reciprocal transport, we see this non-reciprocal transport in the when the vortices inserted by the external magnetic field becomes very clear. So when vortices are somehow allowed to move, so because this is a very two-dimensional superconductor, vortex spinning is so weak, so it's very easy to move around, but it works as it moves in the non-central symmetric potential.
I see. So it's the motion of the vortices.
Motion of the vortices
I see.
Rectified by this crystalline potential.
Very interesting. Very interesting.
This is somehow combined aspect between this vortex matter and
yes, I can see that. I see. Thanks
Sorry,
very much.
For a poor explanation.
No, it's very clear. Thanks very much.
Okay, so now let me move on to our outline of this today's talk. So up to now, I have introduced you about what I'm going to talk about. And then I'm going to speak about intercalation-induced two-dimensional superconductivity in a particular material, zirconium nitrogen chloride. This is also a layered material. And following this, I'm going to discuss about the two-dimensional BCS-BEC crossover. So let me introduce this material. As you see here, this is a zirconium. This is a layered material. Zirconium. This is somehow this forms a double honeycomb lattices. So each layer is a formed by zirconium and nitrogen, and it is stuck. So it's similar to the boron nitride, but it's somehow double honeycomb structure somehow forms the automatically sandwiched by this chlorine atoms. So this layer is surrounded by chlorine and stacked with each other. So this space is forms a van der Waals gap. Of course, we are able to cleave it into a very thin layers. But today I'm going to speak about only some of multi-layers. And even in multi-layers, we are able to intercalate potassium ions. In this particular case, lithium, we are able to induce the superconductivity. So the band structure calculation is like this. So they have a very nice parabolic conduction band at the K point, same as that of the Mori disulfide. They have a very nice parabolic conduction band minimum at the K point and minus K point. And we are able to change the Fermi energy by changing the amount of lithium and the from 0 to a very high level. So as you see here, the density of state is very flat and reflecting the two-dimensionality of this material. So more than 10 years ago, people have established a phase diagram using the bulk material, bulk polycrystalline material, lithium X zirconium nitrogen chloride. And basically, the TC is almost flat as a function of X, in other words, carrier density, because as you saw in the previous page, density of state is basically flat. That's why since the TC is controlled by mainly by the density of states, it shows almost a carrier density independent TC. However, people realize that the TC goes up with reducing carrier density. It is very weird considering the almost flat carrier density of state again. So, but to go beyond the limit of the low carrier density limit in bulk state, it was very difficult. So that's why we introduced the graphene technique and try to access the superconductivity. So this is a cleaved flake. Thickness is 20 nanometer. We didn't care too much about the thickness at that time. It's more than 10 years ago. And we made this device and we put the liquid on top of it. And we saw this gate-induced superconductivity. What we did here is the carrier gating on top of the topmost surfaces, and with this with this field-induced superconductivity, it's highly two-dimensional. If you apply magnetic field perpendicular to the plane, it is easily destroyed. Superconductivity is easily destroyed. If you apply a magnetic field in plane, it becomes very, very robust. So if you plot the HC2 as a function of the magnetic field angle, so it shows a very sharp peak near the in-plane magnetic field. So this is one of the very nice demonstration of the highly two-dimensional superconductivity of gated materials. But our interest is on the carrier density dependence. So this is a comparison between bulk and electrostatically gated superconductivity. So this is the bulk superconductivity as I have shown you in the introduction part. And this is the phase diagram obtained by the gating. In sharp contrast to this bulk data, TC goes down with decreasing the carrier density. This is weird. Why it doesn't match with each other? But the important thing is that we are interested in the increase of TC rather than the decrease of TC. So we are excited with the two-dimensional nature of the gated superconductivity and investigated many things. But in terms of this carrier density dependence, we are not too much interested. So we decided to go back to the bulk material or multi-layer materials and lithium intercalation. So there are two modes of ionic gating. The electrostatic gating is the one we have first tried and proved the two-dimensionality. So here, ions are distributed only on topmost surfaces without introducing lithium in the interlayer spaces. But we are able to make another mode, which is electrochemical mode or intercalation mode, in which we exclude the distribution of the ions on topmost layers, but limit only intercalation. So how we can do this? So now this is a picture. We make exploration, make several tens nanometers devices, and make somehow lithography to make this type of contacts. But for intercalation modes, we cover almost all the layers of the device except for the edge of open using the PMMA polymers, so that ions can go, lithium ions can go from the edge, only from the edge, no distribution on top of the layers. But in contrast, in the case of electrostatic gating, we cover most of the layers except for the channel area. That's why ions can distribute only in the topmost layers, and we are not, ions cannot penetrate from the side because every layer is covered by PMMA. So then in this device, using this device, ions are prohibited to access the topmost layers, but allowed to be intercalated from the edge. This is how it works, how the device works. With this, we gated the voltages at above some critical field. Intercalation takes place. Above this, we are able to continuously control the lithium content concentration, and also this concentration can be measured by the Hall effect. But we are also very much interested in approaching the low carrier density limit. So in this intercalation process, this change is very sudden. So it's really difficult to catch the very low carrier density region. We have a very much difficulty to reach the low density region, low carrier density regions. But my student, Yuji Nakagawa, realized that the deintercalation process in the reverse process occurs relatively somewhat gradual. So gradually. So with this, he realized that we are able to capture the low carrier density regions. So using this, we measure the Hall effect, rho by x versus magnetic field, and if you change this slope indicates the carrier density. From this, we estimate the x value, lithium x, number of the lithium, assuming the lithium ions provide 1 electron to zirconium nitrogen chloride layer. So the low carrier density region can be only reached by this deintercalation process. With this, we measure the temperature dependence of the resistivity. Starting with this non-doped state, by intercalation, we are able to reach superconductivity. And if you zoom this region up, we see continuous quasi-continuous change of carrier density. With decreasing carrier density, TC indeed increases, and at some point it starts to decrease. So this is a summary of the phase diagram, TC versus carrier density or lithium concentration X. So it shows some peak here at the density of almost 1%. So down here, we are able to access in bulk. but below this, we are not able to access in bulk. But only with gating, with a using single crystal, multi-layer single crystals, we are able to reach this maximum of the TC. And a good thing for material scientists like us is that the maximum TC here was something like a 13 or 14 Kelvin in the bulk material. But with device technique, we are able to increase the TC, although it is a slight increase, like a 4 degree or 5 degree. But this is a maximum TC within this series of materials. That is what we are delighted about. But also we realized a very interesting features, particularly in the HC2. So this is the HC2 for two materials. One is this 5% material, and the other is a 20% material. Relatively large carrier density. This is relatively low carrier density. So anyway, it is basically very anisotropic. Even though if you see this, this is for perpendicular magnetic field. This is for in-plane magnetic field, parallel to the plane. And it's already highly anisotropic. But if you reduce the carrier density to 6%, somehow the temperature dependence for in-plane HC2 is changing qualitatively. This is similar to somehow root T behavior, square root T behavior, and this one shows somehow linear behavior. This is nothing but a signature of the 2D-like superconductivity, which we have also seen in the gate-induced superconductivity. So even in the intercalated superconductors, we see a crossover from 3D to purely two-dimensional. This is one important thing. But why? This is still layered material, multi-layer. There should be interaction between the layers. Why? So this hint was given by this theory group. They have been investigating about the 3R structure of MOS2, which is a different material, but the stacking pattern is the same. This is also rhombohedral. Our stacking is also rhombohedral. They said that at the K point, interlayer interaction hopping is exactly 0. So if I speak about the only in our zirconium nitrogen chloride, from this theory, they said that interlayer nearest neighbor interaction hopping integral is exactly 0. Second nearest neighbor is also exactly 0. So the finite interlayer hopping is allowed only to the third layer, which should be extremely small. That's why this is a peculiar feature of the rhombohedral structure at the K point, exactly at the K point. What we are doing by reducing carrier density is this. If the carrier density is high, the Fermi energy is somehow distributed far from the K point. But by reducing the carrier density, it's getting closer to the exactly K point. That's why interlayer interaction is dramatically reduced by reducing the carrier density, and then it becomes somehow more and more two-dimensional. This is what is occurring in the multi-layer systems in the rhombohedral stacking. And another important feature obtained from the HC2, out of plane HC2 this time. In the previous pictures, we have been discussing about the out of plane behavior, but in plane behavior, in plane HC2 behavior. But in this case, we discuss about out of plane HC2. Out of plane HC2 keeps increasing with decreasing the carrier density. So if you plot the HC2 as a function of the lithium concentration or carrier density, it was continuously increases, although a signal to noise ratio is not too good. But in other words, the coherence length at zero temperature can be estimated from this. In-plane coherence length keeps decreasing, maybe as small as somehow 5 nanometers. And if you make this plot, KF 1 over KF Xi, which is a ratio between the Cooper pair size and the inter-electron density, inter-carrier density. So it started from 0.01, which is nothing but the BCS layer, BCS region. So Cooper pair, many Cooper pairs are overlap with each other. But by reducing the carrier density, overlap is getting smaller and smaller. And here in this limit, only 2 or 3 Cooper pairs are overlap with each other. So this is indicating that indeed we are approaching to the BCS, BCS-BEC crossover region. Anyway, it's very different from the BCS limit. So from this, we are going into the tunneling spectroscopy. So in the superconductivity study, tunneling is very important because we are able to look at the superconducting gap. But in order now, our device is covered by the PMMA polymers. So we are not able to measure some STM. So, but we are very fortunate that we are able to measure the tunneling spectrum because now we are dealing with the semiconductor doped with electrons, right? This is doped semiconductor. In the contact region of the electrodes and the superconductor regions, since it is a semiconductor, there is a Schottky barrier formed. So using this Schottky barrier at the contact, we are able to measure the tunneling spectra, as seen here in this in the hafnium analog of superconductors. So it shows a very nice coherence peak, and this is nothing but evidence of the occurrence of superconductivity. We apply this technique, of course, to our zirconium nitrogen chloride system. In this case, we fix at the lowest temperature. Temperature is fixed at 2 Kelvin, and it changes the carrier density from 13% to less than 1%. From this, we can say that the delta keeps increasing with decreasing the carrier density, which is also very interesting. And this is the 2 delta over KBTC, which measures the coupling strength of superconductivity. So it increases from the typical weak coupling BCS limit, which is 3.55 to almost 6. So with the decreasing carrier density, coupling is also increased. We are very happy with this data because, as you see here, this is a polycrystalline material, which we have been working on 10 years ago. And using this polycrystalline materials, we are able to obtain delta values using the specific heat measurement. From this specific heat, the tendency was something like this, which is continuously connected to our device data. So we became very confident that we are capturing the very intrinsic feature, which is continuously connected to the bulk. So now we are able to plot delta over EF, also the KF Xi. So this is a delta over EF. This is 1 over KF Xi. So this data somehow shows almost the same data. And this means that particularly in this delta over EF. Delta over EF is almost 1/3 or 1/4, one third. So this means that superconducting gap is just 1/3 of Fermi energy. This is very amazing situation. And let me show this first. So now in the BCS regime, the delta is much smaller than EF. But now our 2 delta is comparable to EF. So, that data clearly shows that we are now in a very different region from BCS, which we believe in the BCS-BEC crossover region, because delta is comparable to EF. So BEC limit is the other limit from the BCS. We are not able to reach this limit yet. At least we can say that it's in the we are in this region. Another important feature we have found is that this. So in this particular material with less than 1%, 0.66%, the TC of this material determined by the resistive transition is about 18 Kelvin. Even above 18 Kelvin, you see a very clear gap feature in the tunneling spectroscopy. From this data, we plot that the delta is preserved up to this very high temperature comparing to the resistive transition of TC. So if it is truly BCS, it should go like this. But in terms of the superconducting gap, nothing happened around here, but keeps going up to preserved up to T star. So this is a resistive transition for the same sample. And this in the case of 13% samples, the resistive transition occurs at 11 Kelvin, and the gap closing occurs almost at the same temperature. So in other words, by reducing the carrier density, this pseudo-gap state is largely enhanced. So if you summarize the phase diagram, temperature versus carrier density, we are able to draw this phase diagram. So it at 13%, the gap opening temperature and the superconducting transition temperature is almost the same. But at the below 1%, around here, the gap opening temperature is much higher than the superconducting transition temperature. So between this, we believe the pseudo-gap phase is formed, in which pair is formed, but it doesn't condense into a coherent state, the superconducting state. This phase diagram is also very somehow very nice to me, because the carrier density, the phase diagram established in bulk is also somewhat consistent with our device data. Oh, it's already 50 minutes, 50. So we should close the session. But is it really two-dimensional BCS-BEC crossover? In order to show this, we plot the phase diagram like this. So delta over TC is scaled by this Fermi temperature, and this carrier density is changed to delta over EF, obtained by the tunneling spectroscopy. And this is a plot of the theoretical plot. Important thing is that in the three-dimensional case, the TC over TF converges at almost 0.2. But in our case, it is almost 0.12. What is the difference? We found the theory paper for the two-dimensional BCS-BEC crossover. They predicted that the TC should converge at 125, 125. But in reality, if they go into a very deep two-dimensional BEC limit, it forms a peak. So this theory finishes at this peak, but if you expand this region, it slowly goes down because it is log scale. But anyway, it shows a peak at the peak point is 0.125. In other words, 1/8. So observing this 1/8 and Pseudogap is a benchmark of 2D BCS-BEC crossover, which is very much consistent with our experimental data. From these comparisons, we came up to a conclusion that we have realized a two-dimensional BCS-BEC crossover. Right after the publication of our paper, authority theorist Carlos Sademero tried to fit our data with a very simple theory using this Hubbard-like model, tight binding model, with an attractive interaction, and the succeeded to fit our data, but somehow failed our BCS region. This is a carrier density versus TC, very nicely fit, but this region, they failed to fit, and so they didn't describe. So according to Carlos, he said that they are not able to fit BCS region very well because this theory, he neglected the retardation effect, he said. But I don't know. But anyway, even this simple theory can explain this theory fit. But he needs to do some more work on to understand the pseudogap state, gap opening temperature. So let me, before summarize my talk, let me consider from the viewpoint of superconductors. This is a critical temperature TC plot as a function of Fermi temperature for many kinds of superconductors. So in the end of the last century, Professor Uemura from Columbia University made this plot, and he claimed that this is a BEC region. This is a BEC plot for 3D, and this is 2D. And he said most of the so-called exotic superconductors nowadays are located relatively close to the BECS limit, in contrast to the conventional element superconductors, which is deep in the BEC region. This is BEC region, and this is this is BCS region. This is BEC region. And nowadays, recently, physicists are discovering new materials which is existing right close to the BEC region, twisted bilayer graphene, iron selenide, and the monolayer iron selenide, reported by these papers. And our data is existing around here. So we started from this deep inside the BCS region and crossovering the this exotic superconductor regime and approaches to the BCS-BEC crossover, BCS approaching to the BEC limit. So this is somehow, with this, we'd like to summarize my talk. So I think I have introduced you what BCS-BEC crossover is using this gate-induced superconductivity in zirconium nitrogen chloride. So we introduce a benchmark of the two-dimensional BCS-BEC crossover, and we have confirmed, we have shown our observation of the BCS-BEC crossover. Thank you very much for your kind attention, and thank you for a very careful listening. Thank you for this opportunity again.
Thanks very much. That was a very interesting talk. We're open for some questions now. If anybody has some questions. So perhaps I'll start with a couple of questions first. So this is very interesting that it seems like you're able to actually control this region of pseudogap region by decreasing your doping density. By decreasing your doping density, you find actually a very large kind of kind of region of pseudogap region, and this probably is in line with the fact that you're going into more of a strong coupling regime. So do you have any understanding of what the pseudogap phase might be? You also say in your summary slide that this material has no magnetic instabilities, no CDW phases, and so this is quite different from the high TCs,
right?
Like the cuprates, and there are all these competing theories in the cuprates which try to explain the pseudogap phase in terms of some kind of competing phase.
Yeah.
Right. So could you maybe comment a little bit about your system, what you think the pseudogap phase is in your system, and maybe
Okay. So in fact, there are many there are many for instance, the pseudogap is have been reported in several systems, something like this. For instance, this is a cuprate. So carrier density versus temperature, they saw a large pseudogap state. So this system is some very typical example of the very complicated systems with so variety of kinds of instabilities, magnetic instabilities, also charge density wave state instabilities, so complicated situation. And in other systems, this is a lead atomic layers, and they change the thickness of this lead film formed by their special MBE technique. This is from Chin-Hua's group. They said that this is a TC, and this is the gap opening temperature. So they saw some pseudogap as well. So I think this is free from the this type of complexity, free from magnetic instability or charge density wave instabilities. So it's seemingly that in the two-dimensional case, the pseudogap can be tend to be formed. This is very different from the case of correlated insulating systems. If you come back to our system, as I told you, as you said as well, this system is somehow a very simple parabolic system, no complicated band structure, and absent of the magnetic or charge density wave state, many instabilities are absent. So it's a free electron system in short. Even in this free electron systems, two-dimensional systems tend to form a pseudogap state. Why? So if you have a interaction between the two fermions, if you have for instance, some interaction, it could have a attractive interaction like a BCS mechanism. But in the case of 3D, it's not clear, it's not obvious that they can have a bound state in 3 dimensions, even if the interaction is very, very weak or high temperature, the temperature is very high. However, in the case of 2-dimensional systems, once you have a attractive interaction, it could form a pair. Because of the low dimensionality, the 2-dimensional system, the fermion, 2-dimensional fermion could form a pair. Attractive interaction always form a, this is a two-body problem. It's not a many-body problem. It's a two-body problem. Two-body interaction, they can have a pair. That's why in a 2-dimensional system, if you cool it down, maybe it tends to form a boson-like state. This is somehow what we are thinking about, and in the theory predicts like this pair forming temperature, the pair formation temperature. This is because this is enlarged because it is 2-dimensional, which is totally different from the other cases.
I see. I see. So you're saying that in 2D, just because of its dimensionality, however arbitrarily weak your potential is, but it's actually not weak. Your potential is probably quite strong. You'll always be able to form a pair. Whereas in 3D, it's it's a detail question. It's you have to fine tune and make sure that it's large enough.
Exactly. But it is a two-body problem, not a many-body problem.
Yes, that's right. A two-body problem. So this is on the BEC side, because then each.
Yeah.
I see.
So in other words, two-dimensional system easier to access the BCS. Sorry.
The BEC.
BEC, yes.
Yes. I see. That's very interesting. So Alexander had a question, and then we'll go to Weipo.
Unmute. Thank you for the very interesting talk. Please, could you show your tunneling spectroscopy data again at low carrier densities? Here, perfect. Thank you. Now, at your lowest carrier densities here, your zero bias conductance is enhanced, and your coherence peaks are very wide, which is indicative of an enhanced Dines parameter. So a short quasi-particle lifetime and increased scattering. Do you think this could be indicative of some type of emergent heterogeneity in your samples?
Oh, that's a very good question. Yeah, I couldn't pay too much attention to it because, first of all, we are not, our measurement of the tunneling spectroscopy is not the ideal, way. The state of the art, we are far from the state of the art STM, right? Sure. We are just using a very classical method, and the Schottky barrier is not the ideal insulator. So we didn't pay too much attention about the details of the tunneling features. If this reflects the somehow intrinsic nature, I will be very happy. But at the moment, I'm not very confident. So, for instance, it never goes to zero conductivity. I believe this is due to the imperfect insulating nature of the Schottky barrier. Sure. So I'm sorry, I dare not to discuss about this in detail.
It's fine. The reason that I asked is because I'm sure you're already aware there are lots of theories that predict that in this strong coupling regime and in the low carrier density or effectively high disorder regime, you should get some kind of phase separation. I wondered if at very low carrier densities, so even lower than what you showed in your diagram, do you have an intermediate metal state between your insulator and your superconductor? Okay. Can you see a Bose metal in your data? That's my last question.
Oh, that's a very good question. Sorry. For up there.
Yes, exactly. So
up there, we are always these regions are metallic behavior.
Yep, but if you go to even lower carrier densities, can you ever suppress? Can you ever exactly? Can you ever suppress superconductivity?
Yeah,
and then you get a metal or an insulator.
This is what we are trying to do. So still, we have difficulty to reach below this. Okay. For material scientists like me, the direction to decrease TC is not exciting very much.
Oh, this is exciting. This is very exciting.
But this is interesting. Yes, I agree. Yes, maybe we should be somehow patient.
Thank you very much.
Thank you very much.
It's very interesting. So we had a possible question from Weipo. You raised your hand, Weipo.
Yes. Thanks for the nice talk. So you mentioned the 2D material, right? So in this twisted graphene is also very close to this BCS-BEC region, right? So yes. Can you comment on the possibility of this transition there?
Yes, they have already done very nice work, and the published Nature paper. This one.
I see.
They in this particular case they used a tri-layer. So this tri-layer paper is this one. And they are changing the band filling in this axis. This is a TBKT, goes a maximum and reduces. They are able to kill the superconductivity. So this is realizing even idealistic situation, as pointed out by Alexander. So and they didn't care too much, pay too much attention on this region, but in their case, they are observing. I believe they are observing very peculiar things around here. In reality, so this is the coherence length they have obtained. I can't remember how they obtained this. This is from HC2. This is from HC2. So they found that the increase of GL coherence length in a huge the increase. So what I have seen until here is that in our experiment is going down, keep going down up there. But in their case, they observe this increase, broadening of coherence length. They have been discussing something about this in the paper. Maybe you can go there.
Okay, thanks.
More questions from students, maybe? Postdocs, undergrads? Let me just ask one final question. So, apart from this whole kind of, pantheon of very interesting things that might happen, for example, in strong coupling, this Bose metal, for example, that Alex talks about, and pseudogap phase. There's also another one which you kind of, showed a little bit in that small little backup slide that you had called strange metal. Mm-hmm. And I wonder if you measured high temperature on the kind of higher doping side, but higher temperature. Do you see any indications of strange metal? Because you're saying that the pseudogap phase is an inherent kind of thing of 2D, nothing to do with CDWs, nothing to do with magnetic instabilities, and so some other people have different theories for the 3D cuprates, but they also have different theories also for strange metal as well. They say strange metal could arise from some kind of fluctuations in the system, of some magnetic instability or something. And I wonder if you, in this case here, super simple system, right? Super parabolic system, so none of all these complications. Do you also see strange metal as well? In particular, do you see linear and T resistivity?
Good, very good question. But I don't think we have seen a very some T-linear like strange metallic behavior in these regions, and we have been always we see somehow. I cannot conclude that it is too square because somehow our distributions, data distribution is too large about the exponent. But it's definitely not just one. Always we saw somehow square-like behavior, and I was very curious about this metallic behavior below this T star, but even below this P star, we didn't see any anomalous behavior yet. I don't know why somehow anomaly at this T star is missing in the resistivity data, but maybe we should make an additional experiment in different angles, not only from resistivity but also from a thermal conductivity or this type of thing. We need more data maybe.
I see.
And,
I see.
Yeah.
I see. So it's not just the exponent that has to be at T. I think at some point. The amount of dissipation, they always talk about these Planckian limits in the strange metal phases, and so it's called Planckian limit. It's called the Planckian limit. So the amount of dissipation, in these strange metals start to approach the largest amount of dissipation you can ever have in any kind of microscopic system. So there is I can send you these papers, but there's a thing called a Planckian limit. So it doesn't have to be linear in t. It could also be t squared, but there may be this thing. Just a question. That's all. Yeah.
Okay. Yeah. Thank you so much. But maybe I should.
Yeah. No. This is the reason I ask is because it's a very interesting, very simple system that can be used to probe very difficult physics. But okay, any last? Sorry.
Your anomalous metal means around here or
yes.
around here? Around here.
Yeah, around on the right hand side. That's right. Okay. Yes, on the right hand side.
There are several possibilities of anomalous metals over here.
Yeah, there are very many ones. Yes, that's true. Yes, Bose metal as well, for example. So there's all these things. Yeah. Okay. Are there any more questions? If there are no more questions, let's thank Professor Iwasa. This was very interesting. Thank you for your time. To come and talk with us.
Yeah. Thank you very much for this opportunity. Yeah.
Thank you. Thanks very much.
Good afternoon.
All right. See you. Bye.
Bye-bye.